Okay, so this is part three of the this introductory video about some basic statistical concepts. So the first two parts we kind of went over the idea of a distribution, right? And we also in part two we went over the concepts associated with a population and sample, right? The fact that we don't have data from everyone in the population, so we get data from a sample, and based on that sample, right, we calculate some characteristics, maybe a sample mean, to try to estimate the population mean. Right, the issue is, right, each time I generate a random sample, the sample characteristics probably changes a little bit. They're probably going to be pretty close to one another, but they're not the same. So let's take a look. Right, so when you have a variable of interest, right, so far we've looked at things such as height of girls, or the wages of American workers, right? Let's say wages, well, wages don't follow normal distribution. Let's say the heights, right, follow a normal distribution. Then if you take, right, different samples of size n, so maybe n could be 50, right? So if you keep taking random samples of size 50, right, from the population of teenage girls, then the sample means, right, from each random sample. So what's happening over here is, right, you have your first random sample of size 50, right? The sample mean here, I'm going to put x bar, and I'm going to put a subscript 1 to represent that it's from the first sample. Maybe that average height was 63.7 inches, right? And then you take a second random sample with n equals 50, and then your sample mean for your second random sample is maybe 64.3, right? And then you take a third random sample, right, of 50, sample mean, maybe it's going to be 65.8, right? So we expect these random samples, the sample means, to be maybe a little bit different from one another, but they're going to be pretty close to one another, right? So what we're saying is, if you were to then create a histogram of all of these random samples, so far over here I've only written up to 1, 2, 3, but let's say you obtain many of these random samples. Then these random samples, right, we create a histogram of these random samples. The histogram will follow a normal distribution with mean mu, so the mean stays the same, but now the standard deviation is divided by square root of n. It decreases. So that's what the sampling distribution means, right? It's basically the distribution of your sample means over here. So in the previous slide, we say if your original variable was normal distribution, then the sample means will follow a normal distribution. This part over here, this slide, is talks about the central limit theorem, and this is one of the most consequential theorems in statistics. So it basically says that if you have a quantitative variable, right, that has a certain mean and a certain standard deviation, and it's not necessarily normal, but if your sample size is large enough, then the distribution of the sample means, right, of size n will be approximated by a normal distribution, right, with mean mu, standard deviation given by sigma over square root of n. So this is a very important result, right? Is that the implication with this central limit theorem is saying if we have a large enough sample size, we can use the normal distribution to find probabilities associated with sample means, right? So the reason why we like the normal distribution is we know how to calculate a probability from a normal distribution, right? We integrate that PDF, and there's plenty of software out there that will do that integration for us. So that's really cool, right? So basically, even if your original data was not normal, the sample means will follow normal distribution if you have a large enough sample size. One question that people ask is, well, how large is large enough? Basically, the approximation works better and better as your sample size gets larger and larger. So in many books, you might see some suggestions of 25, 30. There isn't really a hard and fast rule, because the thing about such a hard and fast rule, it kind of gives you this idea that, oh, if 25 is big enough, then 24 is not good, right? But basically what we're saying is that 25 works better than 24, and a sample size of 26 works better than 25, right? But there isn't this like hard division between 25 and 24. Now let's see how we can apply some of these ideas to perform some of these probability calculations. So this is a data from previous semester, and students were asked how much they spent on textbooks for that semester. So this is the histogram for for our students. The mean is $405.57. Standard deviation 210.59. So this is a histogram, right? So you can kind of see this is not a normal distribution. This is what we call a right-skewed distribution because a lot of the data points are lower, right? And then you have a few of these data points on the right extreme over here, right? That's why we call it right skewed, because it's extreme on the right side. So most of the students, right, spend about between $250 and $500. And then you have a few maybe very generous scholarships that allows them to spend up to $2,000 on textbooks. But this is a right skewed distribution, right? So we can't use a normal distribution to describe this shape. But what happens if, right, you are interested in, right, talking about the sample mean, right, rather than the distribution of of the amount of textbooks that they spend. So let's say we take repeated samples of size 25 from this population, right? So that previous histogram represents the data from all the students. If we keep taking repeated samples of size 25, what is the distribution for the sample mean? And what happens if you have repeated samples of size 50? So, right, with n equals 25, right, the sample mean, I'm going to put x bar, and I'm going to put in subscript n equals 25 to represent that I'm talking about samples of size 25, right? We'll follow normal distribution, right? The mean is going to be the same. It's going to be 405.17, and the standard deviation of these sample means will now be 210.59 over square root of 25. And if you work out this numerical value, this is going to be 42.118, right? And with us, if you take repeated samples of size 50, their sample means will follow normal distribution, right? The mean is still 405.17. Standard deviation was the original sigma over square root of the sample size 50. And if you work out this standard deviation over here, this standard deviation is equal to 29.782. Right, so this is this calculation over here. So these are the distributions, right? The means are the same, but the spread, right, of the smaller sample size is larger, right, than the spread of the larger sample size. So let's take a look at some pictures, right? So basically from the previous histogram, I keep taking repeated random samples of size 25 and then find the sample mean, right? So your first sample mean of size 25 maybe had a certain value, right? And then I take another sample mean, find its own value, it varies, and then I plot the corresponding histogram for all of these sample means. So this was the shape, right? So if you were to try to, you can kind of see it can be approximated by a normal distribution. With size 50, right, it looks like this is the normal distribution that we can approximate it by. You notice the spread for the smaller sample size, right? This is more spread out than those values over there. Now let's see how we can perform some calculation over here. So let's say you have a random sample of 25 students. What's the probability that the sample mean is less than $415? So let's kind of work this out over here. Right, so we did already establish that the sample mean with sample of size 25 follows a normal distribution with mean. I'm going to just remove the units here, right? 405.17 and standard deviation of $42.118. So now the question is that we are being asked over here, right? What's the probability that this sample mean is less than $415? So this is how we write it in probability notation, right? So P represents probability. It's probability that your sample mean is less than $415. So how we work this is we convert all of these to a z distribution. So what we're going to do, right? So how we convert this to a z distribution is to subtract the mean and then divide it by the standard deviation. Right? So I applied this same operation by minus the mean divided by 42.118 on both sides of this inequality. So 415 minus 405.17 over 42.118. Right, so these two statements are the same, right, because I performed the same operation on both sides of the inequality. Now remember, right, we said that if we standardize something, it follows a normal standard normal distribution. So this left-hand side is basically the standard normal distribution. So this is basically saying probability that you have a standard normal distribution value less than, and then this numerical value on this right-hand side of this inequality, right, if you work it out, this should work out to be 0.233. So what's the probability that in a standard normal distribution, right, the value of your standard normal is less than 0.223? So how do we visualize this? Well, the next thing you should do is to sketch your standard normal distribution centered at 0, right? And your z-score over here is 0.233, right? So it's basically what's the probability of a standard normal that's less than 0.233. So again, probabilities, we can just shade this entire area, and that is the corresponding area that we want to find. So we did say that, right, what one could do, right, is to then do an integration from negative infinity to 0.233 and then integrate the probability density function of a standard normal with respect to x. So this will be done, you know, in the good old days. The good thing is, right, there are software that will allow us to compute these values here. The way to find this value over here is you could use R. In R, we will type pnorm. So the function that we use is pnorm, and then you just input your z-score. And this will give you the percentile associated with z-score of 0.233, right? And if you actually type this out, what you'll get is the following. So let me just erase this over here. If you type that in, you would have gotten 0.5923, right? So this area here, 0.5923. So notice I used the word percentile. So percentile means, right, the probability to the left, right, which is what we want, right? We want z distribution less than this z-score, right? So that's what we want, right? So this probability is now 0.5923, right? So that's how we could perform this calculation. So it's basically saying, right, the probability of having a sample mean with size 25 of less than $415 is about 59% over here. So that's this particular part over here, right? The next part of the question asks, what happens if you have a sample of size 50? And the calculations are still pretty much the same, right? So you establish that the sample means of size 50 follow a normal distribution, mean 405.17, and standard deviation given by 29.782. Right, and then we kind of follow the steps that we did earlier on, right? So the probability that this sample mean is less than 415, standardize both sides, so we get probability minus 405.17 over 29.782, right? And then the right hand side, we take 415 minus 405.17 over 29.782, right? And this chunk here, this basically follows a standard normal distribution. So probability that your standard normal distribution is less than, and if you evaluate this value numerically, this has a z-score of 0.3301, right? So standard normal 0.3301, right? We want probability that is less than that, so this is the shaded area we want to find. And if you work this out, this is 0.6293, right, by using, and then we type pnorm, our z-score is 0.3301, right? This will give you this value over here, right? So that's kind of how we work some of these probabilities over here. So, right, so even though our textbook spending, right, the data for the students did not follow normal distribution, but the sample means will follow normal distribution. So this is just a exercise for you to work on. I would encourage you to try this out, and we'll post the solutions somewhere for you to refer to. Right, so where do we go from here, right? So what we've seen, right, we know now that the sample mean, right, describes our particular sample, but we collect another random sample, its sample mean will probably be different. We do know that with a large enough sample size, right, the distribution of the sample means can be approximated by a normal distribution. And what we have actually seen also, right, is that the standard deviation decreases as sample size goes up. So the sample means will be closer to the population mean on average if you have a larger sample size. Now, what happens in reality, though, is that you don't know the value of the population mean. So look at the previous examples. We've assumed the value, that we know the value of the population mean. So in reality, how do we actually use, practically speaking, the sample mean to estimate the population mean? And that's where we'll go into the next couple of video slides to look at.